So the next topic is linear equations and Bernoulli equations. So let's first see the definition. Today we are going to see linear equations. In the next video we will see Bernoulli equations. A first order differential equation is linear in the dependent variable y and independent variable x if it either is or it can be written in the following form: dy dx plus p of x y equals q of x, where p and q are functions of x only. For example, you look at this equation: x dy dx plus x plus 1 times y is equal to x cube. This is linear, although the equation itself is not in this form, but you can turn it into this form by dividing throughout by x. And when you do so, this is what the equation becomes: dy dx plus, if you divide x plus 1 by x, you get 1 plus 1 over x times y, and that is equal to x squared. Here this p of x part is this 1 plus 1 over x, and q of x is x squared, both of which are functions of x only. That is why the original equation is linear, and actually this one is also linear. The main result about linear equations of first order is theorem 2-4. The linear differential equation, this one, has an integrating factor of this form: e to the power integral of p with respect to x, where p is this function of x. If you multiply the equation on both sides by this integrating factor, then you can solve it, and doing so you get the following one parameter family of solutions. Y times, you can see it for yourself. If you multiply the equation on both sides by this, then the left hand side actually turns into the derivative of y times this, the integrating factor, and that equals the right hand side, which is the product of q of x and the integrating factor. And then when you integrate both sides with respect to x, the left hand side is what did I say just now? This is the ddx of this. So after integration, the left hand side turns into this ordinary product, y times the integrating factor, and the right hand side becomes this. After multiplication, the right hand side is integrating factor times q of x. So when you integrate that, you get the integral of that with respect to x plus an arbitrary constant c. And it can be proved that this family of solutions actually has all the solutions of the original differential equation. This last fact, however, is not proved here, but a proof of this theorem you can find in the text. It's a very easy thing. I mean, you can see it for yourself. Just you multiply both sides of this equation by this and see that, then that modified left hand side equals the derivative of this. That's it. Now, instead of looking at the proof, I am leaving the proof to you. It's available in the text. We are instead going to see 3 examples where we will see some linear equations and we will solve them. So this is example 214, where we have to solve this linear equation, which is dy dx plus 2x plus 1 divided by x times y equal to e to the power minus 2x. So we start the solution by first writing the given equation is linear, okay, and the integrating factor, we give it a name also, say I, is this: e to the power integral of p of x with respect to x. Because it's a little cumbersome to write this as exponent, so we write the notation exp to denote the exponential function instead of the usual e to the power. Same meaning. Now we simplify it a little so that we can carry out the integration nicely. So we divide by x, so that way we get 2 plus 1 over x. Integrating 2, you get 2x. Integrating 1 over x with respect to x, you get ln of mod x. You already know these things. And then you use one of the properties of exponential function. E to the power 2x plus ln of mod x equals e to the power 2x times e to the power ln of mod x. Because these are inverse functions of each other, so mod x comes outside. Now in the text, for some reason, the author has simply written x. This of course we can only do when x is positive. So I am assuming that here x is positive. So that way we get x, in place of mod x we write x times exponent of 2x, which is just e to the power 2x. Now there is no problem in writing this notation. So this is what we are getting as the integrating factor. And now we are going to multiply both sides of this equation by this, and then let's see what happens. So we write multiplying both sides of our differential equation, which you can see I have written here, so that we can see what we are doing by I, that means our integrating factor, which is x times e to the power 2x. So what will you get if you do the multiplication? Here you will get x times e to the power 2x dy dx times, if you multiply x times e to the power 2x by this, after cancelling x, you will be left with this 2x plus 1 times e to the power 2x y. And on the right hand side, originally you have e to the power minus 2x. So cancelling that with e to the power 2x, you will now have x here I mean. Now this turns out to just be the ddx of the integrating factor times y, as was mentioned in the theorem 2.4, and you can see it for yourself. Instead of trying to see how this comes from here, you just straight away do differentiation using the product rule. If you differentiate, I mean you have to differentiate one of these three factors at a time, right? So if you differentiate x, then you are getting e to the power 2x times y. You have that here. If you multiply this with 1, you have that thing. If you keep x and y as they are and differentiate e to the power 2x, then you are getting 2 times x times e to the power 2x y, that you have if you multiply this with this. And then if you keep x and e to the power 2x as they are and differentiate y, then you get this times dy dx. So yes, the left hand side is this. And now it is a very easy thing to just simply integrate both sides with respect to x. Doing so, you get this on the left hand side, and the right hand side is just the integral of x with respect to x plus an arbitrary constant. So this becomes x square divided by 2, and then you can write the function y by keeping y separately and transferring everything else to the other side. That is, you divide both sides by x e to the power 2x. So that way you get y equal to 1 divided by 2 times, after cancelling this x with x square, you are left with 1x times e to the power minus 2x plus c divided by x times e to the power minus 2x, where c is an arbitrary constant. So that is the one parameter family of solutions of the given differential equation, and according to the theory, this has all solutions. Next we have example 2.15, where this time instead of a single differential equation, we have an initial value problem, an IVP, which of course you know consists of a differential equation and initial condition. The differential equation this time is this: x square plus 1 times dy dx plus 4xy equal to x, and the initial condition is this: y of 2 is equal to 1. That is, when your independent variable has the value 2, then the unknown function y, which we have to find, in fact that's what we are trying to do, right, will have value 1 at that input 2. Because the previous solution was formally written with everything, I mean writing all the sentences properly, this time we are not going to do that. We straight away do the calculations. First we turn the equation into that form where we can recognize that it's a linear equation, and we have to divide both sides by x square plus 1 for that. And note that we can do this division because x square plus 1 is not equal to 0. Previously also we dealt with having x in the denominator, but there we had to assume something, that say x is positive or something. Here you need no assumption at all. For no real number x will this ever be equal to 0. So now this is in this form dy dx plus p of x y equal to q of x. So it's the linear equation, and we straight away next go for calculating the integrating factor, which is the exponent of integral of 4x divided by x square plus 1 with respect to x. We take 2 outside because if you do so, you have 2x here and the differential of x square plus 1 is 2x dx. So, the integral will be ln of, we should have written mod x square plus 1, but because x square plus 1 is always positive, you can just simply write x square plus 1. And then you know this property of logarithms, that if you have 2 here, then it goes inside and becomes the exponent of the thing whose logarithm you are taking. And then after cancelling exponent and log, this is what you get, x square plus 1 whole square. This is your integrating factor. So, now you have to multiply both sides of this equation by this integrating factor, and then you can continue your calculation. I have kept this equation here so that we can see which equation is being modified. So, you multiply both sides of this equation by our integrating factor, which is x square plus 1. So, that way you get x square plus 1 times dy dx plus, after cancelling 1 x square plus 1, you have 4x times x square plus 1 times y, and on this side also you have x times x square plus 1, and then the left hand side becomes ddx of integrating factor times y. There is no need to verify every time that this is actually equal to this. The theory, that theorem ensures that that's always the case. You can just simply write this. So, it is that fast. And the right hand side, we do the multiplication so that it helps us to integrate afterwards, x cube plus x, and then we integrate both sides with respect to x, and that way we get x cube when integrated gives us x to the power 4 divided by 4. Simple power formula. Similarly, x square becomes x becomes x square divided by 2 plus an arbitrary constant c. And now do not forget that we are solving an initial value problem. So, now we have to use the initial condition, and the initial condition was this, y of 2 equal to 1. So, you use this here, you put x equal to 2 and y equal to 1, and that gives you an equation. You just put them here, and from that equation you will find that c is 19, and then you use this value back in this equation, and that gives you the solution to the IVP, which solves not just the differential equation but the initial condition as well. Next, we have example 216. Here the equation is given in differential form, not in derivative form. The equation is y square dx plus 3xy minus 1 times dy equal to 0. Let us first turn it into derivative form and then see if it is linear. So, turning the equation into derivative form, this is what we get, dy dx equals y square divided by 1 minus 3xy. No, it is not linear, with y as the dependent variable and x as the independent variable, because this does not have that form. Neither is it linear, nor is it homogeneous, nor is it separable. But then what do? Are we not able to solve this equation by any of the known methods? Yes. If we just look at this equation from another point of view, it will be linear. This one is not linear. In this form it's not linear, but let's see what I mean by that. If instead of finding dy dx, we find dx dy from here, then that equals 1 minus 3xy divided by y square. Now, after you do the division on the right hand side, it becomes this 1 over y square minus 3 divided by y, because 1 y gets cancelled, times x, and then you add this to both sides, and that way you get dx dy plus 3 over yx equal to 1 over y square. Now, in this equation, the form is this, dx dy plus p of y, a function of y only, times x is equal to q of y, another function of y only. So, although this equation is not linear with the dependent variable y and independent variable x, this other equation is linear with x as the dependent variable and y as the independent variable. Can we do this? Yes. Recall that when discussing first order equations in differential form, where you have m dx plus n dy equal to 0. At one point the author mentions that any one of the two variables can be regarded as the dependent and the other as the independent. So if you cannot go anywhere with y as the dependent and x as the independent variable, you can interchange their roles and see if that works. In this case, that works. And now you can go for solving this differential equation as the linear equation in the usual way. And I am leaving that to you, but I will write what the solution is. Here that means you have to find the integrating factor, which will be e to the power integral of 3 divided by y with respect to y, and then you multiply both sides of this equation by that integrating factor and run the usual process. If you do that, this is what you should ultimately get. X equals 1 divided by 2y plus c divided by y cube as the solution, a family of one parameter family of solutions to this equation and hence to the original equation, where c is an arbitrary constant. And this is all we have in linear equations, and in the next differential equations video we are going to see Bernoulli equations, another class of equations which can be turned into linear equations, and then we can solve them.